I will draw this diagram again. We have been talking so far about the triple point. Let us shift to any of these lines. When I draw the black pen means what? This is how it was. Blue, black, red. The same phases were there. Sillimanite, kyanite, and andesite. Now, let us move in to this line. What is this line? It is where both kyanite and sillimanite coexist. Kyanite and sillimanite coexist. If I write it, an equation, I will start getting into it now. Al2SiO5 kyanite is equal to Al2SiO5 sillimanite. That's the reaction. So then, if you know this, then you should know at equilibrium, Gl2SiO5 in kyanite is equal to Gl2SiO5 in sillimanite. That means delta G of the reaction is equal to product minus reactant. Gl2SiO5 sillimanite minus Gl2SiO5 kyanite equal to 0. Gl2SiO5 in sillimanite is equal to Gl2SiO5 in kyanite minus sign, so delta Gr at equilibrium value should be equal to 0. And this delta Gr will be a function of pressure and temperature. Right? It will be a function of pressure and temperature. Now, back to Gibbs phase law. F is equal to C minus P plus 2. What is my C? I'm writing with the black pen. Al2SiO5. 1. How many phases? 2. Plus 2. Variance 1. Means what? How many variables do we have? How many variables do we have? Pressure and temperature. Because composition terms don't come in. Composition terms don't come in. So pressure and temperature. Right? Correct. So it means one of the variables, remember, del GRPT is equal to 0. That means G is a function of pressure and temperature, as I told you. That means if you know temperature, you will find out pressure, or pressure, you will not know temperature. This guy is telling you, this phase diagram guy sitting on the table, on the blackboard, is telling you, boy, folks, you have one equation. It's telling you we have one equation. You have one reaction. What is that? Kyanite is equal to sillimanite. And you have one equation. Del Gr is a function of pressure and temperature. You have one equation and two variables. I can't find both for you. Go to hell. I can't find both for you. Go to hell. Give me one, I give you the next. I assign a temperature value and I get you the pressure value. Assign a temperature value, that means T is equal to something. T is equal to something. You give that equation, give me that value. T is equal to that value. Give me that value. And I will tell you what is the pressure, because I have an equation. But if you give me the T value, I give you the pressure value. Or if you give me the pressure value, I give you the T value. What? I can't give you both. The system cannot give you both because you have only left one equation. No more. Right? But, if you use the red pen, right? How many equations will you have? You will say, sir, I have 3. Now let me tell you, what are the equations you will have? Let me give you an example. You will have kyanite is equal to sillimanite, yes or no? You will have sillimanite is equal to andalusite, yes or no? And you will have kyanite is equal to andalusite, yes or no? Why? Now you see a trick here. Although you see 3 reactions, they are all not true. I will tell you what true means. You see, if I take this 2 and eliminate S, I get back this. Have you understood? If I take this 2, eliminate S, I will get this. So this equation here is a derivative. It is not an independent reaction. It is, it's an algebraic addition to 2 equations. If you look at it this way, I take these 2 equations and eliminate the common phase, I get this. So you see, although you see 3 reactions, out of which 2 reactions are independent, one reaction is an algebraic addition of the other 2 independent reactions. Other 2 independent reactions. This is a very, very important point. I will elaborate it in my next lecture. But the important point that I want to make, although you see 3 reactions, all 3 reactions are not independent reactions. 2 of them are independent, 1 is dependent. So in effect, if you're using all 3, you're going back like a dog biting its own tail. You go round and round in the logic. So here, it doesn't work. You have 2 independent reactions. Choose any 2. You don't have more than 2. So, what does this Gibbs phase rule now tell you? For if you have this phase diagram, it tells you this will be 2. Isn't it? Because this will be 2 minus 2 plus 2 equal to 2. So this will not be univariant, but it will be bivariant. Have you understood? Bivariant. That means this will be bivariant field. That means its position, which was unique for this black pen, now moves over space because of additional variables. What are the variables? XAL kyanite, XAL sillimanite, XAL, and the loci, it is variable. So the position of this reaction is not unique as in the black one. It's not unique. The position is changing. So now you see here, if I draw the same line here, you can see, I draw the same line. The temperature is still there, but if the pressure was, it would be here, or here, or here, or here, depending on what is the composition of kyanite and sillimanite. Because now your variables are there. What are the variables? Pressure, temperature, XAL, sillimanite, XAL, kyanite, XAL, and andesite. So, based on the variables, any two. So, if you say, okay, this is my temperature and this is my composition, then immediately this is the pressure that you find out. But if you had the same temperature but another composition, you would have another pressure. That is why Gibbs rule tells you, give me some, I give you more. Give me some, I give you more. That is the very essence of the problem here. The Gibbs phase rule is a very, very logical, very powerful tool that immediately tells a metamorphic petrologist, as a professional, where you are standing. What you want to do, what you don't want to do, you be careful at this stage. Right at this stage, wait and think. So this is very, very crucial. So when the Al2SiO5 was pure, this kyanite sillimanite had a line, unique line. But when this became a bicomponent system, then the equation that you were using here doesn't work anymore, and this is the equation that varies. Pressure, temperature, composition. What are the X's? X aluminium in kyanite, X aluminium in andesite, X aluminium in sillimanite, just like I told you before. So now it becomes a more complicated function. So now it tells you that, okay, whatever you do, I want two variables. And I explain this line now starts to move, which had a unique loci, which had a very unique loci in a PT diagram, now moves here. So, although you assign a temperature, that means you reduce the variance, you still have one more variance to contend. And this now is line. So you have to assign now not only the temperature, but also the composition of a phase, at least one. And then your pressure becomes fixed. Say, if you take a pressure, then you can see, if you take this line, and this line varies, you can assign a pressure value, you decrease the variance by 1, but you still have difference in pressure temperature depending upon the position of the isoplate. So you need to give a composition to get the exact pressure. And that is what Gibbs phase rule is telling you, cautioning you, is urging you to give the data. How you will give the data, what you will give the data, that's a different thing. That we will do later on. But that is what the Gibbs phase rule says. So this kyanite sillimanite is moving in a binary field. In a binary field. Do you know in a pressure temperature field, its loci is no fixed. Its loci is moving as a function of the composition. And so if you want to get a pressure value or a temperature value, you have to give two additional variables so that you get it. And that's about it. So this is what happens. This is what is very crucial for you to understand. Now, you can imagine. Will it? Okay. Now, what happened? Oh. Blue pen. Even this is not enough. Even this is not enough. Now your kyanite sillimanite becomes a multivariable system. Now you see, you will have 3 minus 2 plus 2, and this will be 3. Do you see that? So now then, you can't use even a binary diagram to show you. You have gone into a multi-component system. Even the simple minerals, you have gone into multi-component systems, where actually the reaction curve is more now a surface on a multi-dimensional space. Not a binary space, not a ternary space. It's a multi-dimensional space. And you need more variables to constrain the position of the kyanite is equal to sillimanite line. You need a lot of a 3-dimensional space to draw the surface of the plane. The last one was a line when it was pure phase, then it went into a surface, and now it's still a surface, but in a 4-dimensional system. It's a 3-dimensional system. Now previously you still could work with a 2-dimensional system when you had red, but now with the blue, you're off. You're gone into what is called abstractism. That's why metamorphic petrology is so complicated. But very logical. It's absolutely logical. There is no uncertainty. There is nothing to mug up. It's just that you have to understand it. And things are done. You don't have to read a lot. Of course you read a lot, but what I'm trying to say is you don't have to memorize in metamorphic petrology. Absolutely nothing. Just like in structural geology, don't memorize. Don't memorize. It's no use. Stress strain diagrams, whatever you take in structural geology, pure shear, simple shear, you can take fracturing. You know, what is there to memorize in structural geology? Nothing. There's nothing to memorize in mineralogy and crystallography. Nothing. Absolutely nothing. If you had to memorize, there is something wrong with the system. Metamorphic petrology, you don't memorize. The moment you have to memorize, you're gone. Don't try to get it from memory. Just take it as it comes. Okay? I think we will stop here. I hope I've been able to impress upon you the importance of system components and phase components. Metamorphic variables, how they work. Next, we will come to a very, very important, interesting thing. And that I will do in the 5th lecture. Thank you.